Hello everyone, my name is Abhishek and welcome back to my channel. In today's video, let's build a very interesting DevOps tool using AI. So basically, one of the very common challenges for DevOps engineers is identifying the infrastructure drift. Creating infrastructure is easy. Today, tools like Terraform can create the infrastructure for you, but the manual changes by developers to the infrastructure creates a drift. And this drift is literally a nightmare for DevOps engineers. In today's video, let's build a tool that can identify this drift. So basically what we are going to build is a Terraform drift detector. Now this is going to be very interesting and I want every one of you to build this. So I'll break this down in 4 simple steps. Step 1, I'll explain you the problem statement. If any one of you is not clear about infrastructure drift, I'll explain this in the step 1. Then in the second step, I'll talk about the tools that we are going to use. We will use the most powerful tools to implement this project. Then in step 3, I'll explain you the complete architecture, end-to-end architecture, and how the components are going to interact. And finally, step 4, we will head towards the implementation. Once again, this is going to be very interesting. So make sure you watch it till the end. And all the useful links for this video are in the description. So make sure you check out the description as well as the pin comment. Perfect. Without any further delay, let's get started. Let's start with the problem statement. What exactly is this infrastructure drift? Let me explain. One of the common DevOps activities today is to create infrastructure. DevOps engineers don't create the infrastructure manually. They use infrastructure as code tools like Terraform. What Terraform does? It takes input from DevOps engineers in HCL file format, HashiCorp language. It converts this HCL file into bunch of API calls. API calls to cloud providers like AWS, Azure, GCP, and multiple other providers that Terraform supports. Now, these API calls create the infrastructure on the cloud platforms. This is the process. Terraform is super cool because now DevOps engineers don't have to learn bunch of API calls. They just have to learn HCL file format. But there is a problem here. Terraform remembers the infrastructure that it created using a file called state file. And this state file updation is unidirectional in nature. When Terraform creates the infrastructure, it updates the state file. But what if some developer or some DevOps engineer manually updates the infrastructure, maybe during an incident, which is very common in the organizations? Now, this infrastructure updation that is done manually is not notified back to Terraform. Terraform does not have a mechanism at the moment, and Terraform does not update the state file. This is called as infrastructure drift. Terraform does not have the latest information of the infrastructure on the cloud platform. And as I told you, this is a nightmare for DevOps engineers. Sometimes they take days of time to fix this. Because there is no official mechanism in Terraform at the moment, we are going to build this Terraform drift detector in today's video. This drift detector can be run as a cron job, maybe once in 60 minutes, once in a day, whatever is the organizational requirement. This identifies the drift and this sends an email notification or shows the drift on the terminal so that DevOps engineers can immediately fix the drift, either by updating the state file manually or by revoking the infrastructure changes that are done manually. So this is the problem statement, and this is exactly what we are going to build, Terraform drift detector. Now let's talk about the tools that we are going to use to build this project. First and the most important one, the AI coding agent. We will go with Cursor 3. So Cursor 3 is the latest version of Cursor. If you haven't used it till now, the user experience is super cool and it comes with very interesting features. For example, with Cursor 3, it is very easy to run multiple agents in parallel. Like you're working on a task, maybe using an agent, you can kick off another to keep moving in parallel. On top of that, With Cursor 3, you can literally build and ship from anywhere. You can use your mobile phone and you can use one of their agents and ship the application. On top of that, switching between local and cloud is also very seamless. Let's say you kick off a long task in cloud. Then once you're good, you can pull it to local, probably add some tests or polish the details. I'll show all of this using the user interface. Then what about the model, the large language model? We will go with Composer. To be specific, we will go with Composer 2.5, which is the most intelligent coding model developed by Cursor. Composer is also very cost effective, and when you are dealing with sustained work, or let's say you are dealing with long running tasks, Composer is very reliable. Now I know what you're thinking, but Abhishek, what about comparison with frontier models? Don't worry, Composer is on par with the leading models on the Sway Bench Pro. Cool. Then what about the cloud platform? Where are we going to create the infrastructure? We will use AWS. And for infrastructure as code platform, we will go with Terraform. Obviously, we are building Terraform Drift Detector. And finally, the coding language, we will go with Golang. Of course, we are not going to write the code, but still it matters because you are building an application. This is a very simple and efficient tech stack for our project. Now let's take a look at the architecture. At the core of the architecture, we have the drift engine. What is the responsibility of the drift engine? It compares the resource information in the Terraform state file against the actual information on the cloud platform. I mean the actual resource information. Now this is tricky because Terraform state file stores the information in the TF state file format, and AWS has this information in the JSON or YAML format. So what we have to do for Drift Engine to compare these things, we have to bring both of them into a common format. Of course, first we have to extract the information and then we have to get them in a common format so that Drift Engine can compare it. So what we will do, we will get both of them into the Ghost structs, right? Because in Ghost structs, we can put this information in a very flexible format rather than bringing both of them into JSON or bringing both of them into YAML format. We will put them in a Ghost struct format, and Drift Detector will compare both the structs and tell us by either providing a JSON report what is the difference, or maybe it prints on the console output, whatever is feasible, or we can do both of them as well. Now for this to happen, there are different components here. Let me walk you through it. First, there is a state reader. What state reader does? State reader extracts the information from the TF state file. Initially, it gets this information in the JSON format, and then from the JSON format, it puts this information in a Ghost struct. Similarly, there is a cloud fetcher. Cloud fetcher makes use of the cloud APIs, in this case, AWS APIs, gets the information in the JSON format, and then the JSON format information is put in the Ghost struct format, right? Now, on both the sides, we have information in a structure. So Drift Engine compares it, generates a report, or prints the output to the terminal. Now, the biggest challenge here, as I told you, is getting both of them in the common format. And this would take a lot of time in general, because first you have to understand all the types of resources. Then you have to prepare a structure. You will have to go through multiple iterations. This would easily take 2 to 3 months of your time. Let's say you are an expert, or if you have worked on a similar solution in the past, this might take 1 month to 45 days for you. Now we will use in the implementation part, now that we understood the architecture, we understood the problem statement and the tools that we're going to use. Now let's head to the implementation part and let's ask Cursor agents to build this entire solution for us. Okay, now for the implementation, we will start with Cursor 3. It's very easy. Just head to cursor.com/agents or use the link in the description. That will get you to this page. Once you're here, create an account. And once you create an account, you can start with creating a new agent. As we learned, you can create multiple agents and you can run multiple agents in parallel as well. Okay, so we will choose the model. first. So I'll go with Composer 2.5. There are different models, but as I told you, Composer 2.5 is token efficient and it is also on par with the frontier models. So I'll go with this. And then I'll select the repository. Now, why are we selecting the repository? Very simple. The cursor agents are capable to create a pull request and push the code to your GitHub repository as well. So like literally you don't have to interrupt in the middle. You can create the whole application and you can push the code to your GitHub as well or create a pull request for peer review. Okay, so I have this empty repository, Terraform Drift Detector. Now cursor is connected to it. Now let's provide the requirement. But what I'm going to do, because this is slightly complex, what we are going to build, first we will create a plan, right? Instead of directly generating the code, we will first create a plan. And once we have the plan, and once we are okay with the plan, only then we'll go ahead and ask the agent to implement the code base. So this is the prompt. Build a Terraform Drift Detector platform that continuously compares Terraform state files against actual cloud infrastructure to identify the configuration drift. The system retrieves expected resource metadata from Terraform state and actual resource metadata from cloud provider APIs. Normalizes both in the common model and highlights the differences such as deleted resources, modify attributes, and tax changes. Users can run scans on demand or schedule and view drift reports through simple dashboard CLI or JSON format. The solution should be cloud agnostic, extensible, and optimized for fast infrastructure visibility without requiring Terraform plan or apply operations. And here I have an option. Let's say for this entire thing, I can also share the architecture diagram, which is good part because we already have the architecture. Like I've explained you the architecture sometime back. I provided the same information here. Now cursor can generate the code much better, but initially I wanted to plan the entire thing before writing the code. Let's go ahead and see how this works. So it is setting up a new cloud agent for us, Composer 2.5, Terraform Drift Detector. On the left side, you can see this new cloud agent. The environment is getting ready, planning the next moves. Nice. You can see here it worked on the plan for 1 minute 45 seconds. It generated the goals and no goals. You can go through the goals and no goals if you're okay with it. Then it again generated a high level architecture from the high level architecture that we provided. This time it provided more detailed architecture. It also shared the core data model, what it is going to build. As I told you, this is the key part. Entire thing is in the Go struct. So it shared the Go struct that it is going to build. And it also provided the component design, like how would the state reader look like? How would the cloud extractor look like? How would the drift engine look like? A high level schema of what it is going to build. And then end of the day, this is going to be a CLI application. So it also named it as Driftctl and it shared the commands for the Driftctl as well. It is going to run these commands internally. That's fine. Or we can also run this Driftctl commands. It also provided an option for cron job. So you can see here, this is how you can run the cron job for it. Then further, it also added the complete workspace structure. So if you're okay with all of this, so this is the plan it generated. If you're okay with it, we can just say, please proceed with the implementation. Or let's say if you need some changes, you can discuss here with the agent and you can further modify it. I'm super happy with it. Please proceed with the implementation. And there are few things here which I would like to mention. MCPs. Right now, we don't need an MCP server for this project, but let's say you're dealing with some information, maybe external to the agent. You can add an MCP server so that agent connects to the external documentation and fetch the latest information. And even if you want, you can provide multiple models. Okay, we are going with Composer, but let's say you want to choose 2 to 3 models. Even Cursor supports it. Perfect. Now let's ask it to go ahead and implement it. Let's see how it implements. Okay, it is implementing the next steps. So you can see the steps it is going to implement. First, it is going to scaffold the Go Meno repo. So entire thing is going to be in a single repository. Then it is going to implement the core model. Then it is going to implement the AWS provider, implement the Driftctl, and finally it is going to add tests, config examples, readme, and it is going to push this entire thing as a pull request to the Git repository. If you want, you can directly push it as well. Also, I want to mention one thing here. This is a cloud agent, so you don't have to wait for this completion. You can go ahead, create a new agent. Let's say you're working on something else. You can start building another application or another project as well. In fact, they have an option for agent demos. Let's say if I enable agent demo for this cloud agent, once agent completes the entire work, it provides a video demonstration for us so that we don't have to review the code base. We can just review the demonstration that agent is created. Like just like how we create demonstrations for the project that we create and present it to our team members, agent can create a demo and share with us, right? So you can go ahead and work on something else. Meanwhile, agent creates this Terraform drift detector. Anyways, going back, I can see it started building the SQLite Go, store.go, provider.go, aws.go. Looks good. Okay, now it says the implementation is complete, at least the first part of the implementation. Let's see what did it build. So it created the state reader, state extractor, AWS provider, drift engine, scan orchestrator. Now it is saying that we just have to go ahead, run the make build. And once the make build is complete, we will have the Driftctl. So we can run this command. This is for, this is just a dry run. And then we have a live AWS scan. We just have to export the AWS region where we have the actual infrastructure. And then we have to run this command so that it provides a information of the drift. Now you might say, but Abhishek, where is the code base? Okay. Cursor agent created all the files for us, this entire structure. Where can we find the code base? You can just head to the GitHub repository. So this is my repository, Terraform Drift Detector. You can see a pull request is created. Implement Terraform Drift Detector platform using Driftctl. And this pull request, this is a very well curated pull request. You can see the complete summary, implements Driftctl, provides the architecture, what's included, how to use this. And if you want, you can also open in Cursor. Let's say someone's reviewing the pull request. They can also open this in Cursor. Probably they can perform the code review. And all the files are here. So this project has a 31 files. All the 31 files are created and pushed as part of the pull request. Now I'll go ahead, merge this, and then I'll download this GitHub repository and then try to execute the Driftctl. Cool. So let's see. I will add myself as a reviewer, assign to myself. Okay. I'll just scroll down. I'm fine with it. Ready for review. I'll change this and merge the pull request. Perfect. So now we have the complete code in the GitHub repository. I'll just go back, Terraform Drift Detector. There we go. With the README file, with the architecture, and with the code base. But before we actually download it and run Driftctl, we need some infrastructure created by Terraform. Let's do that. I have an AWS account. Let's simply create a S3 bucket using Terraform on the AWS. So Terraform creates a state file, and then we can execute the Driftctl. Let me pull my terminal for this. Okay, so I have this terminal. There is a sample Terraform project in here. You can see the main.tf file. Let me open this for you. So the main.tf file, it has the Terraform block, and then it has the provider as AWS. My AWS credentials are already configured, so we don't have to do that. And then it is going to create a bucket. Name of the bucket, my unique drift detector bucket 12345. I just given a random name to it and some simple tags on the bucket. You can see I haven't complicated the bucket creation, very basic configuration. Now let's go ahead and run Terraform. I'll just do Terraform init first. I hope I have Terraform installed and configured. Yeah, good. So now it is initializing the repository for us. There you go. It initialized the project. Now let me run Terraform plan. I can in fact run Terraform apply first, but Terraform plan. Let's see if all our Terraform main.tf file is good and it is going to create an S3 bucket for us. Okay, one resource to add, all good. So now I'll run Terraform apply. Okay, I'll say yes. There we go. It says a bucket is created. Let's verify this on my AWS account. Okay, so this is my AWS account. Let me search for S3. Perfect. So the bucket is created. And we also have the state file locally here, right? This should create a state file for us, terraform.tf state. Don't worry, you can have the Terraform state file anywhere. You don't have to have it here. The application that we created, we can provide the location of the Terraform state file. If it is local, it picks up from the local. Let's say you have it in the remote backend or you have it secured somewhere. The project is capable of reading your state file. Nice. Now let's pull our project. So the drift detector, I'll just copy this. I'll go back to my terminal. I'll switch to the downloads folder. I'll download this using git clone followed by the URL. Perfect. I'll switch to the Terraform drift detector. All good. And now I'll follow the instructions as per the README file. Or I can also look at the cursor agent, but it created the README file. It says all that I need to run is make build. Let me run the command. I'm not sure if I have make installed. Let's see. Good. So I have make installed. It is building the project. Let's wait for it to build the project and then we can verify. Good. So it created the artifact for us. Now we can verify. I'll just do /bin followed by drift. Okay, we have the driftctl here. Now we can follow the instruction. So we want to compare the local state file against AWS. So what we can do, we will provide a scan hyphen state. So scan hyphen state followed by the state file path. In our case, state file is in downloads. Within downloads, we have sample Terraform project. So let me put that here and then the Terraform state file. Okay, then what's the next thing that we have to provide? We just have to say hyphen provider AWS. Okay, and region. In my case, the region is AP South 1. So I choose the region that's nearest to me. Let's run it and see what happens. Wow, that's super fast. You can see here, it says in the summary, total resources are 1. Absolutely. Missing in cloud is 0. Extra in cloud is 0. Attribute changes are 2, which is expected. Tag changes, total findings 2. So what does it say? There is nothing that is serious. Only thing, there is a warning because of the attribute changes. We can ignore that. What's important? These two fields, missing in cloud and extra in cloud. So it says my Terraform state file, the one that I've provided here, is exactly in sync with the resource that is created on the cloud platform. Let's see what I'm going to do now. I'm going to tweak the S3 bucket, right? We will modify the S3 bucket. We will make a minor change or major change to it and see if our drift detector can identify it. So I'll click on the bucket. I'll go to the properties. I'll try to add a new tag here. It's a trivial change, but still, I'll add a tag name Abhishek. Okay, save the changes. Successfully added one user defined tag. Now let's go here. And what I'm going to do now, I'm going to rerun this. Now you can clearly see that total findings have changed to 3. As I told you, this is a trivial change. So missing in cloud, extra in cloud, this did not affect. But apart from warnings, there is an info message that you have to act upon. So it says there is a new tag on the S3 bucket. The value of the tag is Abhishek. So our drift detector is clearly working. It can even respond to the trivial changes like tag changes. Very useful when you're working in production environment or very useful when you're working in a critical environment. Even the tag change is crucial. Now let's finally put this to an ultimate test. So what I'm going to do, I'm going to delete an S3 bucket here, right? So let's say there is a developer or there is a junior DevOps engineer accidentally deleted the bucket or maybe intentionally deleted the bucket. Now this is a major impact, especially if you're working on critical environments. If someone deletes a resource from cloud, and as a DevOps engineer, if you're not aware of it, if your Terraform is not informing you about the change, then it's a crucial issue. Now that we have developed this Driftctl, let's see if it is able to identify it. So I'll run Driftctl again. I haven't changed any parameters. The same state file, same AWS account. You can see here very fast. Like I think it only took less than 2 to 3 seconds. It was able to say missing in cloud is one resource. Okay, obviously when you have more resources, the comparison would take little more time, but Go is usually fast. So you might have this difference in 30 seconds of time. So we can see missing in cloud is one, and it is clearly saying the security risk is critical. The missing resource is my unique drift detector bucket 12345. Just imagine when you have hundreds of thousands of resources on cloud and your Driftctl is clearly able to pinpoint this is the missing resource. This is the resource someone deleted from your team. Wouldn't that be awesome? Yes. So that is our Driftctl. And can you imagine? We have built all of this using cursor agents in, I think, probably an hour of time or little less than that. And even if you look at the observability aspect of it, so if you want to see the amount of tokens that we have spent, or if you see the spending of this project, so you can go to the usage. We literally spent 0.32 US dollars on this. So that is why I've chosen Composer for this project. So Composer is token efficient, as I've already told you. You can see that on the observability aspect as well. So today I just used 0.32 US dollars. Even on the spending, you can find the similar information. Perfect. And you can see our Terraform drift detection is completely merged. And this is a working project. And I made this project open source. You can also go ahead. You can use this project. If you are interested, you can build on top of this project. I'll keep this project open source. Let's collaborate on this and let's build a Terraform drift detector for production use cases. Perfect. So isn't this a wonderful utility? Definitely yes. Personally, if you ask me, every DevOps team should build something like this because infrastructure drift is a major challenge. And if you have noticed in the video, we built this in a super efficient way because we use Cursor 3 in combination with Composer 2. And the best part here is that Composer 2 is token efficient. So you don't have to spend a lot of token in planning and building this project. Once again, all the useful links are in the description. If you want to download Cursor 3 and start using Composer 2 to build a project like this, you can check the link in the description or in the pinned comment. If you have any questions, do let me know in the comment section. I'm more than happy to respond. See you all in the next video. Take care.